Hi and welcome to another edition of Ordinary Differential Equations. We are going to journey to a new landscape. We are going to start a new chapter on Laplace Transform. So let's go ahead and get started. So you're going to hear this expression repeatedly from now to the end of semester. We are going to talk about Laplace transforms all the time. So you might be wondering about what is this transform. Let's go ahead and take a very general look at this before we drown ourselves into all sorts of formulas and such. Laplace transform is going to be another method of doing the problems that we have done, and it has certain advantages that is going to come to light later on. To get a sense for what a transform is, let's go back to what you think it is. So probably what you remember about transformers is a movie by that title. So in this movie, if you take a look at a few I guess that's enough of that. So there's a truck that transforms to this robot back and forth and such. So that is a legitimate transformer. But going to something a bit more serious, where else do you hear about transformers? Of course, you hear about the transformer station being close to your home and such. And the topic actually does come up in engineering quite a bit, where you are constantly transforming energy from one form to another form. So if you go look at where your electricity comes from, typically in many cases it's a hydroelectric station somewhere that's providing you with electricity. So you have a water behind the dam. This water has potential energy. As it pours down, that potential energy transforms to mechanical energy. That mechanical energy becomes mechanical energy of rotation of this turbine. And then in the generator, that transforms to electrical energy. And then you have these high voltage power lines that bring it to somewhere near your home. And then again there is a transformer there that changes the electricity's voltage to something more suitable for in residential usage. Then it comes to your home, and then there are all sorts of transformers there, from your fan to your phone, that transfers that energy to still other styles. So we have some what we have in mind, it has some similarity to this, very vague and general similarity. Before we start looking at the mathematical landscape, let's also mention that sometimes you are trying to get an impression from the world around you. You're collecting data. Well, you do that with your eyes and ears and such. But there can be always some other styles of collecting that information. And for example, a bat uses echolocation to get a sense of how his surrounding looks like. So imagine the ability of, say, kind of a species that perhaps can switch between having eyes and having echolocation. So when it comes to mathematical transformers, what we have in mind is converting some functions to some other functions. So what we are transforming is data, and data we call it a function, and we are changing it from one form to another form. You have already seen some transformers. You probably call them operators. For example, in your calculus classes, most important operator that you have seen is differentiation. So differentiation has a notation. For example, this is one of the notations for the differentiation. This operator takes in some input. Let's give it an input, let's say x to the power of 5, and then it produces some output, and that output is, say, 5x to the power of 4. So this is an operator. This is what it takes in, and that's what it produces. Sometimes you write the input in some general notation, you say call it f of x, and the output you have an abbreviated notation for it. Maybe you write it as f prime of x or something. What we have in mind is something like this, but one level higher up. The operator that we have, now we're going to call it the transformer, is going to be named after Laplace, the French mathematician philosopher. So we borrow the first letter of his name, L, and then we apply it to the functions we encounter, all those pet functions and some other functions. So we are going to have some function. We are going to feed this to the Laplace transformer, and out comes some other function. The new twist to the story is that that new function that comes out is a function of some other variable, unlike this one that x5 and x4 show up here, same x. Here, what the new thing is that this is going to be a function of some other parameter or variable s. It's going to be our customary notation that we are going to start with a lowercase letter here, and after the transform we are going to use the upper case of that, and the input parameter is going to be t and output parameter is going to be s. Okay, let's try to motivate things a bit more still before we dive in all the formulas. What is it that we are planning to do? So in this course we are learning about differential equations. So there's an equation we intend to investigate and solve and such. Well, back in high school we have seen other kinds of equations that were, well, a lot easier than these things. For example, 2x plus 3 equal to 0. That was pretty innocent equation to handle compared to this. One big selling point of Laplace transform is that when you take a differential equation and then you transform it, so to indicate that we are going to transform it, we are going to use this letter L. It takes a differential equation as an input and produces an algebraic equation as the output. You're going to see that in a lecture or two. So imagine the differential equation we have had in this class, like y prime plus 5y equal to, say, exponential of t. That's a differential equation. When we transform it, it becomes an algebraic equation, just like those you had in high school. Actually, it becomes a very simple algebraic equation. Well, due to this simplicity, we can solve this very easily. So from this algebraic equation, we can go to its solution in a matter of a second, in fact. Once we are here, we are going to have a tough journey going back to the previous landscape. So it's like here you're in the echolocation landscape, you are handling your data there, and then you have to take it back to your sighting landscape there. We are going to have something else. It's called inverse Laplace transform. Inverse Laplace transform, from this we are supposed to go back to our so-called time domain. And when we do that, we get the solution of the differential equation. Yeah, so what are we doing? Instead of going straight from the equation to the solution, we are taking a detour. Now, detour, maybe I can indicate it like this. When we take that detour, this is going to be referred to solution by Laplace transform. So solution by Laplace transforms. So we are going to start practicing it today, explaining what actually Laplace transform is, and do some of the preliminary work. And in a lecture or two, we are going to be ready to actually take this detour and solve some equation this style. Of course, detours are never all that pleasant. If you already had a road and you're comfortable with it, and you have been taking that, you're not going to be all that happy to take another road. But we are going to see that there are certain problems that are a lot easier to solve in this style, and also you're going to have a new landscape in front of you. So it's not just solving the equation that we have been solving, rather it's gaining different appreciation and understanding as to what is happening during this process. So let's go ahead and see how transforms show up in mathematics. Laplace transform is one of many different types of transforms that exist in mathematics. So you may be wondering what other transforms are there. Perhaps the most famous of them that you're going to see in your engineering classes is the Fourier transform. Depending on how many mathematics style courses in engineering you're going to take, you're going to see that one as well. And there are perhaps at least half a dozen well-known transforms in mathematics, each of them suitable for attacking certain type of problems. And so perhaps the first the most important two that you see are Laplace and Fourier. But there is also, say, wavelet transform, Miller transform, and so on. Okay, how do these transforms work? We have a certain general category of transforms that are referred to as integral transform. Integral transform, as the word implies, integration is the main mechanism for transformation. So you have some function, and depending on what kind of a transform you have, Fourier, Laplace, and so on, there is some secondary function that's referred to as the kernel. This kernel, let's write it k of two variables s and t. So there is a function that depends on the kind of transform you have in mind, that multiplies the first one, and then there is a integration to be done. That's why it's called integral transform, that starts somewhere and goes to some place, and all of that is going to be integration in t. After the integration, of course, t disappears, and s is the only surviving parameter. So the function that comes out is a function of s, and we might show it as f of s. So this is the general form of integral transforms. Well, what we have in mind is a very special type, and we call that the Laplace transform. Laplace transform goes like this. Well, as usual, we have of f of t. Our kernel is the following: exponential of minus s times t. That's the kernel. for the Laplace transform. And the alpha and beta for the Laplace transform are from 0 to infinity. Integration is versus variable t. It's called the time domain. Out of this process, some other function is going to turn out here, and that function is going to be a function of the variable s, and it's going to be shown by f of s. So one convention is to start with the lowercase letter for the original function and the uppercase letter for the Laplace transform. Another style is to indicate all of this by the following notation: script L, a bracket, then F. You might want to put the variable of F here as well, and then out comes f of s. Now, a Laplace transform is a close cousin of something you see in Calculus 2 under title of so-called Taylor series. There is a close connection between the two of them. Maybe in a future lecture we talk about it. But today we are just going to go ahead and practice this integration to get our feet wet as to what is really meant by this. So we are going to start with some nice simple function for this f, and just go ahead and calculate this integral, and that's going to be our f of s. In that process, we are going to start building up a certain table. So you are going to see me drawing this table over and over again. I will start with some functions that we see quite often in this course, and calculate for each of them their Laplace transform. So starting with the simplest function will be just 1 perhaps. Then we are going to go ahead, maybe look at, say, some exponential functions, some trig functions, some polynomial functions, and mixture of these things. When you look at them, you remember a category of functions we played quite a bit. You remember what name I gave them? Remember P, E, and T, the pet functions. So they resurface here again because they're particularly nice compared to other functions for us to practice this. Of course, the simplest, most trivial function will be 0. If you put 0 here, and that one function also turns out to be 0. So that's not all that interesting. So first non-trivial case will be a constant function. So I'm going to consider a constant function f of t equal to 1, which means for all times it's just stuck at 1. What we want to do is to go ahead and calculate what f of s is going to be. So we're just going to apply our formula. What we are supposed to do is to integrate from 0 to infinity of exponential of minus st times the function, which is just 1, dt, and find out what this integral is going to be. Well, there are certain integration techniques that are going to show up, techniques and formulas that are going to show up very often in this section, so you want to go ahead and refresh your memory on those formulas from Calculus 1, and I'll just do a quick review as well. So you remember that if you have exponential of u du, antiderivative is just e to the u plus a constant. If you have exponential of a number times variable t dt, you remember that the antiderivative is exponential of same exponent but not divided by 2 and the constant, and so on. So substitution and chain rule are going to be standard feature. Antiderivative of exponential of minus st, just like this one, is going to be exponential of minus st divided by minus s. This is the antiderivative of that. Now, aside from doing the antiderivatives, we have to also calculate it at these limits 0 and infinity. So I go ahead want to calculate this integral between 0 and infinity. Let's go and write this thing symbolically, what we are trying to do. So these numbers are replacing t. So I have exponential of minus s times infinity, and then exponential of minus s times 0, and then I'm dividing this whole thing by minus s. Okay, a number times 0 will be 0, exponential of 0 will be 1. So this is the easy portion, and this portion is just 1. How about this one? Exponential of minus s times infinity. What's that going to be? Well, we remember for the exponential that exponential of infinity itself is infinity, and exponential of minus infinity is 0. So if we want something finite, I have to put some limitation on my s so that I don't end up with infinity. So what limitation do I need? I need my s to be a positive number. If it is positive number, then I have exponential of minus infinity, and this portion becomes 0. If s were a negative number, then I'll have exponential of positive infinity, and I'll have infinity again, and that's not going to be easy to handle. So what we are going to do is to make a restriction that s has to be positive. 0 is not going to be acceptable either, because exponential of 0 is 1 and its integral is going to be infinity again. So subject to the assumption that s is larger than 0, this expression becomes, this is 0 and this is minus 1 over minus s, which is simply 1 over s. So what we learn is that if little f is 1, then its Laplace transform is 1 over s, assuming that s is a positive number. So we always have a restriction on s. Typically we have a restriction on s that our formula is good for certain values of s, not all values. Okay, that was pretty easy. Let's go ahead and do some other easy ones. Let's do an example of an exponential. Let's first do a particular case. Suppose I ask what is the Laplace transform of exponential of 2t. Well, what does that mean? By definition, that's the integral from 0 to infinity of exponential of minus st times exponential of 2t, that's my original function, times dt. Okay, let me see if you can go ahead and calculate this integral in a matter of a few seconds. So how would you go ahead and do that integration? Perhaps you want to do the first step of antiderivative and then put the limits on it later on, however you feel comfortable. What's the most crucial step here? Most crucial step, a basic idea from pre-calculus. If you have product of two exponential numbers with the same base, you can add up the exponents. So here, same idea, very simple. I can add up these two exponents, exponential of minus st and 2t dt, and then I can factor and write the exponent minus s minus 2 times t dt. Now I can say this is very similar to what I started there, except that instead of s, instead of this, I have this. I have substituted s minus 2 for s. So the answer, if I do the substitution on the left, I should get the same thing on the right with the same substitution. So if instead of s I put s minus 2 on the right side, also I can replace s with s minus 2. Of course, if you want, you can reinvent the formula from scratch that actually go through all of these steps, but it's a lot easier, and that's one of the advantages we want to use in Laplace transform to be as quick as possible in these type of steps. So if I have these substitution, I have a similar substitution on the right hand side. And of course, over there I needed s to be larger than 0, and here I need to have s minus 2 larger than 0. In other words, s has to be larger than 2. Okay, we did this one. What do you think would be the answer to the following? What if I have exponential of 8t? Can you guess? You have 1 second to guess. What would the answer be? Well, of course, there's nothing so special about number 2. It can be any number there, and it will be s minus 8 as the answer, with the restriction that s has to be larger than 8. Well, in this case, instead of giving answer for a specific number, which is kind of like an old style mathematics, or the mathematics that you see in high school, you want to elevate yourself to level of a parameter. Instead of having specific numbers, we just put a parameter like at, with a being a constant number. What would the answer be in this case? And you have just 1 second to answer. The answer will be 1 over s minus a, with the restriction that s has to be larger than a. Okay, that is one victory for today. That was not that bad. 1 over s minus a, and s has to be larger than a. Notice that this formula is a kind of an umbrella that contains that formula in it. Meaning, if I replace a by 0, well, exponential of 0 is just 1. And when you replace a by 0, this formula becomes that. So this is a more general form of that formula. Well, as these problems go, we are almost at the end of easy examples. Everything else is going to require some amount of work and not so trivial. For example, for sine and cosine, you actually need to spend quite a bit of time to go through a slightly twisted integration process, something that you have definitely seen in calculus, but it's not all that straightforward. Let's go ahead and continue with some other straightforward examples before we go to these. Well, it turns out cosine hyperbolic is a lot easier than cosine. For example, you remember what was cosine hyperbolic? Let me remind you from calculus. What was this thing? It's a very famous function that doesn't get all that attention in calculus, but it's one of those functions that actually do show up in engineering quite often. In many structures, there's a design element that uses cosine hyperbolic. You see it in architecture, you see it in industrial design and such. If you look up the expression catenary curve, let me write it here. Sometimes referred to as the chain curve. You see this function. Well, I'm afraid you might not believe me and not go search it, so maybe I go search it for you. So the word itself in a dictionary, and what you see it in the context of a cable that's hanging between two poles. It takes on the shape of a curve, it sags, and that sag is according to the formula of cosine hyperbolic. So catenary applications, you can see it, for example, in architecture. So some famous architects yeah, they're kind of a love affair with this curve, and so you see their designs in all sorts of places. And so it shows up in physics, it shows up in mathematics, and it's a famous curve. But in calculus, somehow there's so much stuff to cover that this doesn't get enough recognition. Formula itself is very easy: exponential of x plus exponential of minus x over 2. Just two exponentials added, and the graph of it, well, it's a graph of hanging cable, and then you see something like this. Some people confuse it with a parabola. Now it grows a lot faster than a parabola. That's how it looks like. Well, why is it that the Laplace transform of it is very easy? Because, well, we have the Laplace transform of each of these two pieces, and therefore we are ready to do. Before we talk about that, let's quickly refresh our memory that this type of transforms are linear, in the sense that if I have sum of two functions and I want to take a Laplace transform of it, what comes to mind is actually correct also. You can take the Laplace transform of either of them and then add them up. Another property of linearity of Laplace transform is that if you have a function and you go ahead, double it, triple it, and so on, so if you multiply it by a number and then you take a Laplace transform, you can take or factor that number out and take the Laplace transform and then multiply later on. These two properties, very easy to verify for Laplace transform, makes Laplace transform to be a linear transform. Laplace transform is linear. However, this is the end of easy life with these type of operators. If I had f times g, it wouldn't be Laplace transform of f times Laplace transform of g. So these type of formulas only good for addition and subtraction. It does not apply to multiplication, division, exponentiation. None of those things apply here, just addition. So what do we do? Suppose I want to take the Laplace transform of cosine hyperbolic of, let's call it bt. Well, what does that mean? Well, cosine hyperbolic itself was exponential plus another exponential and then divided by 2. Well, according to this linearity, I can break my job into take 1/2 of Laplace transform of the first one plus the Laplace transform of the other one, with piece by piece. Well, the advantage is we already have done this. Laplace transform of an exponential is 1 over s minus that multiple with some restriction. So that's all we need to do. So it's going to be 1/2 of. For this, we already know what the answer is: 1 over s minus b, so long as s stays larger than b. And this one, 1 over, what should I write? S minus what now? Okay, minus whatever multiple you have here, so it's minus b, with the restriction that s has to be larger than minus b. Well, sorry. Go ahead and take a common denominator. How do you take common denominator? Well, first of all, write this thing in a civilized way. It's s plus b. So common denominator is s minus b times s plus b. To cross multiply, so this first fraction becomes s plus b, second fraction becomes s minus b. So this becomes 1/2 of numerator. We just have 2s. Denominator, we have s minus b times s plus b. Why not go a step further? Cancel the 2's, it becomes s. multiply these two, becomes s squared minus b squared. Now these two restrictions, that s has to be larger than b and has to be larger than minus b, you can condense it to s being larger than absolute value of b. Has to be larger than both b and minus b. You can say s has to be larger than absolute value of b. So our table got extended. I strongly recommend that you rewrite this table many times until it becomes second nature. Essentially, you have a new set of formulas to learn, in addition to all the differentiation formulas you learn and integration formulas you learn. You have now a new batch. So you have a bunch of formulas from algebra, then from trigonometry, then from calculus, and now here's this one. So let's go through it again. I write it and you try to pause this and tell me what's on the right hand side. So if I can entice you with a picture of a train, maybe I should do that. What is on the right hand side? What was it? So try not to scroll and push your memory to get the answer. So let's write the restriction here as well. So s larger than 0. Then we had exponential of at was 1 over s minus a. Then we have cosine hyperbolic of bt. I used a different letter so things don't run into each other. S over s squared minus b squared. Now s has to be larger than absolute value of b. Restrictions aren't going to play a huge role for us, but it's good to pay attention that these formulas are not applicable to just any value of s. There is some restriction to be observed. So what do you think is the next one? Well, if you have cosine hyperbolic, why not sine hyperbolic? They are, after all, siblings, maybe brothers and sisters and such, and we expect similar formulas for that one. So let me see if you remember what was sine hyperbolic. Sine hyperbolic of x. Sine hyperbolic is not as illustrious as cosine hyperbolic. That one shows up in all areas of engineering, mathematics, applied mathematics. Sine hyperbolic, not so much. You don't see this in architecture. It shows up in formulas, of course, but for example, cosine hyperbolic is also called a chain curve or catenary, but this one is just sine hyperbolic, which is not something people are going to remember. Sine hyperbolic, very similar to that one. It just, there's a subtraction between these two, and the graph of it, well, the graph of it looks like this. Okay, let me see if I can entice you to finding what is the Laplace transform of sine hyperbolic of bt. You think you can take 1 minute off and tell me what this is going to be? Okay, so 1 minute. In 1 minute you are going to tell me what is a clean-cut formula for sine hyperbolic of bt. Is that right? That's the best way to learn. To go toe to toe with your professor and try to produce things as close to what he's doing at that moment that he's doing it. So you're staying concurrent. Now, well, we learned what the trick is. Exponential of bt minus exponential of minus bt over 2. We break it up into two pieces. So it becomes 1/2 of, we learned the trick, that was 1 over s minus b, and this one is, it became plus b. Same common denominator as before. Now I have s plus b first, and then minus s minus b second. So it becomes 1/2 of, this is 2b over s squared minus b squared. So at the end I have b over s squared minus b squared. So this is b over s squared minus b squared. Okay, to get you going with some of the homework problems that are coming up, let me list a few other of these Laplace transform formulas, and then we are going to do the proof for them in the next class. So perhaps the one that is easiest to motivate is, well, you did the hyperbolic version. How about the ordinary version? That's called, ordinary version is called circular. Circular trig function are just called trig functions because that's what you see most often in high school. So what's the answer for cosine? It turns out all that happens is that instead of this minus, you're going to have the plus. So that is a advantage that we have. It's not entirely new. Look, by the way, the restriction for this thing is still s is larger than b, and here, as it turns out, there is no restriction. There's nothing needed to be careful about. So sine of bt, same story, is b over s squared plus b squared. T to power of n, this is one of the more interesting formulas that come up here. The Laplace transform of this, we have to go through a series of integration by parts. We have done something like this in one of the prior lectures. So if you follow that, you see that the Laplace transform of this turns out to be n factorial over s to power of n plus 1. And for this we need s to be larger than 0. And of course here also s has to be larger than 0. Okay, so this was introduction to Laplace transform. We're going to have some basic exercises. Let me just do a couple of examples before we leave off. So suppose I ask you what's the inverse Laplace, the Laplace transform of, say, t cubed plus cosine of 5t plus exponential of 4t. Of course, just a random mix of functions. Unlikely for all of them to show up next to each other added, but here we are just experimenting. For good measure, let's just put numbers in front of them as well so that we see what's happening to them. So for the first one, factor of 7 stays, the exponent being 3, so I'll have 3 factorial over s to power of 4. 2. For cosine, we had s over s squared plus 5 squared. And for the last one, we have 8 times 1 over s minus 4. So we applied the rule of linearity, and we figured out what the Laplace transform is going to be. More often than not, the issue is to go the other way, meaning if I give you the Laplace transform, can you remember what was the function to begin with? So let's do the following. Suppose I ask you what's the inverse Laplace transform of 1 over s to power of, say, 5. is that we are looking for a function that after you take its Laplace transform, we end up with 1 over s to the power of 5. Well, s to the power of 5 means I must have started with t to the power of 4. So I know there is a t to the power of 4 here. But t to the power of 4 leads to a 4 factorial here. 4 factorial of 24, which have shown up in the numerator. So if it is not showing up here, I need to divide this function by that factorial to make my work to be correct. So we can write it as t to the power of 4 over, say, 24. Let's do another one. Suppose I ask you what's the inverse Laplace transform of s over s squared plus 3. Well, essentially we are going to do these things by table lookup. The formula for it requires complex analysis, which we haven't, most students haven't covered, haven't done. So the way these things are going to be done is by looking at the table and saying which one is a match to it, or taking your function, break it up into pieces until the pieces do match to your table. So if I have 3 here, 3 is taking the place of b squared. So if b squared is 3, then b has to be square root of 3. So this is square root of 3 here, and my answer turns out to be cosine of square root of 3 times t. Let's do another one. Say Laplace inverse of, say, 7 over s squared plus 2. Okay, s squared plus a number, that means my b had to be square root of 2. So if I write sine of square root of 2 times t, here I'll have s squared plus 2. But I'll also have a square root of 2 here. So I need to fix my factors. So we go like this. This would have come from sine of square root of 2 times t. But square root of 2 would have led to a present of a square root of 2 here, which we don't have. So we have to compensate by dividing with it. But instead I have a factor of 7. So I'll have need for a 7 here. After you adjust your coefficients, you might go ahead and double check, make sure your reasoning was correct. You would say, according to our formulas, this would have been radical 2 over s squared plus radical 2 squared. So radical 2 squared is 2. I have a radical 2 here, but it's multiplying with 7 over radical 2 this, and that cancel out, and I have my 7 out here. So either you reason your way to this type of formulas, or alternatively you can make a separate table for going from the right hand side to the left hand side, whichever works for you. Okay, let's keep this lecture at this level, and then we come back next time. We go through more tricky formulas as to where did these ones come from, where did these formulas come from, which requires a bit more advanced integration techniques. What you want to do is to go ahead and take a look at integration by parts again, and we're going to be needing that. Okay, good luck and God bless until the next lecture.